4 billion years ago, Earth was a hostile, primordial environment. For decades, scientists operated on a strict timeline. Complex life began exactly 2.4 billion years ago. That specific timestamp marks what researchers call the Great Oxygenation Event. According to standard scientific models, this was the moment organisms capable of oxygen-producing photosynthesis suddenly emerged, filling the atmosphere with breathable air. The proof for this timeline relied entirely on physical macro evidence. Researchers pointed to stromatolites, early fossilized microbial structures with distinct layered patterns, as the oldest visible proof of living organisms leaving their mark on the planet. Those fossils drew a firm line in the sand. That 2.4 billion year mark stood as the absolute limit of our biological history, dictating exactly how and when we believed Earth's atmosphere evolved to support complex life. Biologists long suspected that life existed on Earth long before that oxygenation event, but proving it meant overcoming a massive physical barrier: Earth's highly active geology, visible in ancient landscapes like the Pilbara region of Western Australia. Earth constantly recycles its own crust. Any rocks dating back 3.3 billion years face extreme tectonic pressure, intense heat, and continuous chemical alteration. As a direct result of that geological recycling, the original biological molecules of early life forms are completely destroyed and baked away. This creates a severe problem for researchers. They are forced to try and distinguish the scattered, degraded chemical remnants of a living organism from the natural non-biological chemistry of the rock itself. Human manual analysis hit a strict limitation here. When researchers look at these rocks, the background geological noise of billions of years of changes is simply too overwhelming. The biological signal gets entirely lost in the static. Finding older life required a completely new method. Scientists needed a way to filter microscopic data points out from under billions of years of geological destruction. The breakthrough arrived when researchers combined high-precision chemistry with advanced artificial intelligence. To give the AI something to analyze, scientists first had to prepare the physical samples. They took these ancient stones and broke them down into their smallest components, shattering them into microscopic molecular fragments. Researchers fed the AI massive volumes of chemical data, training the system to recognize exact molecular patterns linked to biological processes within a chaotic scatterplot. It completely ignored the overwhelming background of non-biological chemistry, leaving only the biological signal glowing through the static. The AI acts as an evolutionary translator. It reads a complex chemical language that is entirely invisible to the human eye. Armed with this newly trained AI, scientists applied the system to some of the oldest known stones on Earth. The results were immediate. The system effortlessly separated genuine biosignatures from the overwhelming chemical noise of the degraded stones. The AI detected subtle, unmistakable chemical signals, proving that biological activity was occurring 3.3 billion years ago. Specifically, the system identified photosynthesis. This pushed the timeline of life back nearly a full billion years before the previously accepted Great Oxygenation Event. This single data extraction rewrote the timeline of how and when complex life developed on Earth. This timeline compares old models with the new reality. Instead of a sudden oxygen spike 2.4 billion years ago, the rise of photosynthesis was a slow, billion-year process. That gradual increase in the oceans was a mandatory incubation period before complex organisms could survive. Researchers can now connect these faint chemical discoveries with later tangible fossil evidence. Multicellular seaweed found in Canada's Yukon Territory is a direct result of that exact billion-year oxygen buildup. Earth's habitability was a long, hard-fought chemical battle. It was dependent entirely on microscopic organisms working in the dark for a billion years. If this artificial intelligence can process massive data volumes to find biosignatures in Earth's most ruined rocks, the methodology can be exported off-world. Space agencies like NASA and the SETI Institute are currently adopting these exact AI-driven techniques for their own exploratory missions. Their target is Mars. They are hunting for scattered chemical fingerprints hidden within the Martian rocks. Mars presents the exact same problem as early Earth. Its surface is covered in rocks that have been irradiated and chemically altered over billions of years, creating an identical wall of geological noise. Before humanity could realistically hope to read the history of life on alien worlds, we first had to teach computers how to read the deepest, most damaged pages of our own planet's history.